Welcome to lecture 2 of electromagnetic waves. So in the previous lecture we have ended up till the discussion on 4 equations of Maxwell. So over here we are beginning with a little historical development of electromagnetic waves, that is history of electromagnetic waves. So if we discuss this the history of electromagnetic waves, so it all started with Maxwell. So it was James Clerk Maxwell who was responsible or was the first to predict the electromagnetic waves, was the first to predict electromagnetic waves. Followed by this came Hertz. So we will be studying Hertz experiment. So Hertz produced and detected electromagnetic waves experimentally at wavelength of 6 meter, at wavelength of 6 meter. Next came up J.C. Bose, most importantly an Indian. J.C. Bose, he produced electromagnetic waves of wavelength ranging from 5 millimeter to 25 millimeter. Produced electromagnetic waves ranging from 5 millimeter to 25 millimeter. And then came Marconi. So he successfully transmitted the electromagnetic waves up to few kilometers. He ended up transmitting electromagnetic waves up to few kilometers. So this is the development in electromagnetic waves that took place. So the next which we are going to study over here is the experimental setup for producing electromagnetic waves, or what is called as a Hertz experiment. So I am first of all making a small arrangement in which the Hertz experiment was performed. So Hertz experiment is based on the fact or the idea that a oscillating charge is accelerating continuously, then it will radiate electromagnetic waves. So it is based on the idea that if oscillating charge is accelerating continuously, then it will produce electromagnetic waves. So over here we are connecting two metallic plates that are going to act like a capacitor. In fact, from these two plates we are hanging out two small spheres which are very close to each other, which we are calling it as S1 and S2. And over here we are fixing a receiver S1 dash and S2 dash. This will act like a receiver S1 dash and S2 dash. So basically the idea is to create a dielectric breakdown of air. So using this arrangement, the P1 and P2, which are the two plates over here, that is plate P1 and P2, this is going to act like a capacitor which is connected to S1 and S2, which is separated by a very small distance apart, and it is connected to induction coil or a high voltage source. induction coil or a high voltage source. So the next thing which we say over here is that over here a dielectric breakdown of air will be created. Dielectric breakdown of air will be done. And the next thing which I stated initially was it is based on the fact, this is a Hertz experiment, and it is based on the fact, based on the fact that an oscillating charge, that an oscillating charge accelerating continuously, accelerating continuously will radiate electromagnetic waves, will radiate electromagnetic waves. So when a high voltage is applied across the metallic plates which are acting like a capacitor, so these plates will get discharged by sparking across the narrow gap. That is, as I stated, the dielectric breakdown of the air will break. So breakdown, dielectric breakdown of air will break, and the spark will give rise to oscillation, which in turn will send out electromagnetic waves. So I'm repeating one more time. When a high voltage is applied across the metallic plates, so these plates will get discharged by sparking across the narrow gap. By sparking across the narrow gap, the spark will give rise to oscillations, which in turn will send out electromagnetic waves. And the frequency of this electromagnetic wave is equal to the frequency of LC oscillation, which is equal to 1 by 2 pi root over LC. The succession of sparks send out of a train of such waves which are received by the receiver, which we have marked as SS1 dash, and this is the frequency of the wave that is generated. So a charge oscillating harmonically is the source of electromagnetic wave of same frequency, and a simple LC oscillator and the energy source can produce waves of desired frequency, that is 1 by 2 pi root over LC. And one more thing that can be noted over here is that electromagnetic waves are transverse in nature and they do not require any material medium for their propagation. So I am repeating one more time that the two plates P1 and P2 are connected to the two spheres which are acting like a very close placed capacitor. They are placed very close so as to create a dielectric breakdown, and then when a very high voltage is applied across the metallic plates, these plates get discharged by sparking across the narrow gap, and the sparking takes place because of the dielectric breakdown of air. The spark will give rise to oscillations, and an oscillating charge accelerating continuously will radiate electromagnetic waves. So the spark will give rise to oscillations, which in turn will send out electromagnetic waves whose frequency is given as 1 by 2 pi root over LC. So now we are dealing with the next aspect. So we have seen the experimental setup for producing electromagnetic waves and the basic properties associated with it. So now let us go to the explanation of electromagnetic waves using Faraday's law. So using Faraday's law. So the four equations of Maxwell's were stated as cyclic integral of B dot ds is equal to Q enclosed by epsilon naught, which was Gauss law for electricity, followed by the Gauss law for magnetism, that is cyclic of B dot ds is equal to 0. And in the Faraday's law it was stated something like this, that cyclic integral of E dot dl is equal to minus of d phi b by dt. So we will try to apply this and obtain certain results for the electromagnetic wave. So if we consider that the three mutually perpendicular axes that is this one is the y-axis, the x-axis in which the electromagnetic wave is propagating, and the z-axis in which the variation of magnetic field is taking place. So this one is for the variation of electric field E. This is for magnetic field variation, which we refer as B. And I am considering a rectangular path ABCD in the xy plane. So when I say that I am considering a rectangular path in the xy plane, I mean to say something like this. So we are considering a rectangular path in the xy plane while applying Faraday's law. So this point I am marking as x1, and this is the point which we are marking as x2, and this is the loop which we are talking about, that is A, B, C and D respectively. So over here the length which we are specifying is that this length is written as L2, and we are writing this length as L1. So if we apply this particular set of law for this particular loop ABCD, so I am solving the left hand side of the equation first. So if we begin solving the left hand side of the equation, so before that I can write that the variation of electric field along the y-axis is written as E naught sine of omega t minus kx, and the variation of magnetic field along z-axis is written as B naught sine of omega t minus kx. That is, both of them are traveling in the x-axis direction, which is the direction of propagation of electromagnetic wave. So if we apply LHS for this ABCD loop, that is line integral of E dot dl, so I can break this for different length segment like this. E dot dl, we begin from AB, then next we write E dot dl for B to C, then next we write E dot dl from C to D, and then next we write E dot dl from D to A. So if we look at this particular aspect over here, so I say that for A to B and C to D, the value of E dot dl will be 0, since E is perpendicular to the length L2. So since it is perpendicular to the length L2, so for the length segment AB and CD, the E is perpendicular to both of it, and hence the value will cancel or will become equal to 0. Now for the part B to C and for D to A, so I say that in B to C, the direction of electric field and the length are in the same direction. So the value will be positive, and over here the electric field and the length segment, that is D to A, is in the opposite direction. So the value will be negative. And hence I can say that the cyclic integral of E dot dl for B to C will be positive, and the value of E is at x2 into L, and for D to A it is negative, that is E at x1 into L. Now E at x2 and E at x1 can be obtained by putting the value of E in this particular expression, that is Ey is equal to E naught sine omega t minus kx. So if I take E naught common and L common, so at x2 we write it as sine of omega t minus k x2 minus of sine of omega t minus k x1. So this is the left hand side of the expression that we obtain E dot dl. This is the left hand side of the expression which we have obtained by applying Faraday's law or E dot dl in the loop ABCD. Now we come to the right hand side of the expression. So if we come to the right hand side of the expression, So now over here I am again redrawing this particular axis. This one is x, this one is y, and this one is z. Now the variation of magnetic field is towards the z-axis direction, that is B is directed in this direction, and we are asked for the calculation of the rate of change of flux, and this is the loop which we are talking about, A, B, C, D. So at a distance x, I am selecting a thin patch dx, and we will be calculating the magnetic flux due to this thin patch, that is dx, and the length which we have taken is L1. So we take this length as L1 and this one as L2. So the value is changing from x1 to x2. So if I write the variation of magnetic field, so the magnetic field is varying along the z-axis as B naught, and it is propagating in the x-axis direction omega t minus kx. So at a certain distance x, the value of magnetic field is equal to B naught sine omega t minus kx, and the value of the small patch area is equal to L1 into dx. So if I write the magnetic flux, that is phi b, through this small patch, then I will write it as B naught L1 sine of omega t minus kx dx. So this is d phi, or the small flux from the selected area, that is the yellow marked area in this particular part, that is this one. So this is the area which we are talking about, dA. And if I integrate this expression, then I will get the net flux, and the variation of x is from x1 to x2. So the variation of x is from x1 to x2. So the net magnetic flux phi net is going to be equal to B naught L1 and we are left with integration of sine omega t minus kx dx from x1 to x2. So we have an expression like this, and since we are integrating with respect to x, so the integration of sine will turn out to be minus cos, and we will divide the expression by k. So we divide the expression by minus k, and this turn out to be minus cos omega t minus kx. The limit is from x2 to x1. So if we put the value over here, we get B naught L1 by minus k minus cos omega t minus k x2 plus cos omega t minus k x1. So in order to calculate the entire value of the right hand side, that is we are calculating minus d phi b by dt. So I need to differentiate this expression with respect to time, and we put a negative sign also. So d phi b by dt. So if I differentiate this expression with respect to time, so I will get the term of omega outside, and the derivative of cos will turn out to be minus sign, and hence the expression can be written as B naught L1 upon k, that is we have adjusted this negative sign. So derivative of cos is minus sign, so this value of will become positive sine of omega t minus k x2, and omega will come out, and minus of sine omega t minus k x1, and again omega will come out, which we have already taken common. So this is going to be the right hand side for the expression which we have calculated. So the left hand side of the expression is this one, that is E naught L sine omega t minus k x2 minus sine omega t minus k x1. That is, this is the left hand side for the expression, and this one is the right hand side of the expression, that is minus d phi by dt is written in this sense. So now over here we have already stated in the lecture 1 that the speed is equal to coefficient of time upon coefficient of x. So if this is the speed of a electromagnetic wave, that is c, so I can substitute this omega by k over here as c. And if I equate the left hand side and the right hand side of the expression, so we will attain something like this. So the value can be written over here as that E naught is equal to C B naught. So from both the expression we obtain E naught is equal to C B naught, where C is equal to omega by K. So this entire expression, that sine omega t minus k x2, this entire expression inside this bracket followed by L1 will be cancelled over here, L into sine omega t minus k x2. So we will only be left with E naught on the left hand side, and on the right hand side we will be equal to C B naught. That is what we have written over here, that E naught is equal to C B naught. So from the LHS and the RHS expression, from the Faraday's law, we establish a relation between the E and B which are mutually perpendicular to each other. So now post this we are applying Ampere's law in another rectangular path which will be placed in the xz plane. So if we consider such a path over here, so we are applying Ampere's law. This one is the modified Ampere's law which we will be applying. So again I am drawing the coordinate axis. So this is my x-axis, y-axis, and this is z-axis. And the electric field is in the y-axis direction, variation of electric field, and the variation of magnetic field is in the z-axis direction, which we have already mentioned. And in this case we are taking a rectangular path in the xz plane, that is something like this. So we are taking it in xz plane, something like this, where this point is the value of x is x1, and on the other point the value of x is equal to x2. This length is equal to L2, and this length is equal to L1. So over here if I mark the point, then it is equal to E, F, G and H, which we are selecting. So this one is E, F, G and H respectively. So and if I write the expression for electric and magnetic field variation, then electric field variation along the y-axis direction is equal to E naught sine of omega t minus kx, that is it is propagating in the x-axis direction, and that of magnetic field is equal to Bz is equal to B naught sine of omega t minus kx, it is also propagating in the x-axis direction. So if I go with the modified Ampere's circuital law, which we are stating over here in this manner, that is the Ampere circuital law, which is the modified Ampere circuital law, the fourth equation of Maxwell is B dot dl is equal to mu naught I plus mu naught epsilon naught of d phi e by dt, where phi e is the value of electric flux. So for this particular part, we are first of all solving the left hand side of the equation. That is, we are calculating the cyclic integral of B dot dl for the path EFGH. So if we are applying it for the path EFGH, so we are beginning like this, that we are breaking it into the four segments. So the first segment is between the length EF, the next one is between B dot dl is from F to G, the next is from B dot dl G to H, and the next one is from B dot dl, that is H to E. So if I consider this path, so for EF, the value of magnetic field and the length segment are parallel to each other. So over here they both are parallel to each other. In case of FG, the magnetic field and length segment are perpendicular to each other. In case of GH, the magnetic field and length segment are opposite in direction to each other, so the value will be negative. And again in case of HE, the value is perpendicular to each other, so the dot product value will be 0. So in this case, I can say that for FG the value is reduced to 0, that is they both are perpendicular to each other. And in case of HE the value is reduced to 0, that is again they both are perpendicular to each other. So if we modify this expression for the circulation B dot dl, then we write it as, so from E to F the value is positive, so magnetic field at a point x1 into length L1, and for the length segment G to H the value is negative, so magnetic field at a x2 into length L1. And if I write the value of B x1 and x2 respectively, so we can put the value over here and obtain a value equal to B naught L1 can be taken as common, so we will be left with sine of omega t minus k x1 minus of sine of omega t minus k x2. So we are keeping this expression like this, and we are calling it as the first equation, which is the result of solving the left hand side expression for the modified Ampere's circuital law. Now we are talking about the right hand side of the expression. So the right hand side of the expression is basically about the value of electric flux. So I am redrawing this diagram over here one more time, the three coordinate axis. So this is x axis, y axis and z axis respectively. The loop which we are talking about, that is EFGH, is somewhat like this, that is E, F, G and H respectively, and the electric field is pointed in the upward direction. So the electric field is pointed towards the y direction, that is somewhat like this. So at a distance x from origin, we are selecting a patch of thickness dx. So we are selecting a patch of thickness dx, and this length is L1. Over here this one is x1 and this one is x2, which we have already mentioned in the diagram in the previous page. So over here if I write the value of electric flux phi E, then we can write it as equal to E dot ds, which is the area, and the value is ranging from in this way. So if I put the value of the ds segment, then it is equal to L1 into dx, and the value of x is from x1 to x2 respectively. So if I substitute the value of electric field variation along the y-axis, that is Ey is equal to E naught sine omega t minus kx. So if we substitute this expression, so we get it as equal to E naught L1 integration of sine of omega t minus kx with respect to dx from x1 to x2. So on integrating this particular expression, we obtain phi e as equal to E naught L1. So now integration of sine will turn out to be minus cos. So minus cos of omega t minus kx, and since it is with respect to x, so we divide by minus k over here, and the ranging is from x1 to x2. So if we substitute the value in the expression, so the value of phi e will turn out to be E naught L1 by k with a negative sign minus cos of omega t minus kx2 plus cos of omega t minus kx1. So this is the expression that we have over here. So if we calculate d phi e by dt, so on calculating or differentiating the expression of electric flux with time, so if we are differentiating this expression with time, so omega will be coming common from both the parts, so we write it as omega by k, and derivative of cos will turn out to be minus sign, so the expression will change sign. So sine omega t minus k x2 minus sine omega t minus k x1. And on the right hand side, the value of conduction current, that is if we look at the previous page, so the right hand side is consisting of mu naught I and mu naught epsilon naught of d phi e by dt. So mu naught I is not going to contribute anything for this expression since there is no conduction current. So the value is going to be mu naught epsilon naught of d phi e by dt. So from here I can say that the right hand side of the expression will be equal to mu naught epsilon naught times of d phi e by dt, and hence the expression is going to look like mu naught epsilon naught. So over here one thing is also clear, that the speed of this wave is going to be coefficient of time upon coefficient of x, propagating in the positive x direction. So we will be putting this value of omega by k as c. So mu naught epsilon naught omega by k is written as c, followed by E naught L1, followed by E naught L1, and then we have this expression of sine of omega t minus k x2 minus sine of omega t minus k x1. So we attain this particular expression over here, and if we look at the previous page over here, we have attained this value as b naught L1 sine of omega t minus k x1 minus sine of omega t minus k x2, and if we use this expression over here, this one is a negative sign that is missing, so this is the expression 2 that we have. So if I equate the left hand side and right hand side for the expression, so I can write in the next page in a way like this, that for vacuum there is no conduction current, and hence the expression cyclic integral of b dot dl is equal to mu naught epsilon naught times of d phi e by dt. So if we put in both the equations which we have calculated, so we will find out this expression is coming out to be mu naught from equation 1 and 2 that we have evaluated. The expression is coming out as B naught is equal to mu naught epsilon naught C E naught. So if you look at the two equations which I am again showing you over here, so the value that we are calculating for is equal to this particular expression, that is expression 2, and this one is expression 1. So if we equate both of these terms, and the term inside the bracket is going to cancel each other out, the term inside the bracket is going to cancel each other out with a negative sign. L1 will be cancelled from both the expression, and then B naught will be equal to this particular value, that is mu naught epsilon naught C E naught. So we attain this expression. Now from while solving Faraday's law, so from Faraday's law, so we have already attained E naught is equal to C B naught. So if we put this value of E naught is equal to C B naught in this particular expression, so if we put E naught is equal to C B naught, so it will become C square into B naught. So B naught will cancel out, and from here we get that the speed of electromagnetic wave is equal to C, which is equal to 1 by root over mu naught epsilon naught. So we attain this particular expression, and if we substitute the value of mu naught and epsilon naught in SI unit, it turns out that the speed of electromagnetic wave is coming as 299,792,458 meter per second, which we approximate as 3 into 10 to the power 8 meter per second in vacuum.